So I would kindly ask you to read your statement and then say one or two words about this as introduction. So let's start with the first presenter.
Yes, modeling of cyclic plasticity and phase transformation during repeated local heating events. So for us, it was important to understand, get some knowledge about the material behavior when it is subjected to these local heating events, frictional local heating events. So we wanted to improve our modeling in terms of kinetics of the phase transformation, the description of the thermal strains, and also, more importantly for me, was to describe a proper constitutive model. In this case, it is a plasticity model with Chebauche with mixed isotropic kinematic hardening to be able to predict the material behavior when it is subjected to thermal loading and also rolling cycle loadings later in our later studies. Okay, thank you. The second speaker, please.
So rail fatigue life is more dependent on the rail wear than on track geometry defect. So what we did is a sensitivity analysis of the track geometry with respect to the rail fatigue on our railway network. And what we find is that the dispersion, the statistical dispersion of the rail fatigue life is much more sensitive to the variation of the shape of the profile than on the track geometry irregularities. So for our point of view, for our maintenance point of view, we have to investigate further on the rail profile shape to increase the rail fatigue life.
Okay, thank you. Gerald, please.
Allows to transfer specific RCF-relevant railway operating conditions into experiments. I hope I could show you that, well, it's important, that we have developed a methodology to identify those loading conditions in operation that are relevant for or contribute large increments of damage in a simulation, at least, to crack initiation, and how to define or specify appropriate test rig experiments based on this data.
Okay, thank you very much. And I would now open the discussion about all three presentations, and if there are contributions or questions, so please go ahead. So we have here the first one, and you can also address a specific speaker or all three speakers.
Hi, my name is Rostislav Skrutnik with Chalmers University of Technology. I have a question to Alfonso. For your meta model, how many simulations do you have to carry out to train the meta model?
Yeah, that's one of the most important points of our approach. So when we consider only the geometry irregularities and the rail wear, in that case we have about 1,000 simulations to perform. So it's 1,000 finite element calculation. So, but only then it depends on your computational resources. But if we want to introduce other statistical variabilities for other parameters, so the number of simulations required will increase, and so it could be a problem if we want to introduce a lot of irregularities, but with the sensitivity analysis, we can, for example, we can take off one or two parameters and limit the number of variable parameters. But at the moment, we have about 1,000 simulation for the calibrations, yeah. And this is for one constant radius curves and one train velocity.
Right. So, and my next question is, how often do you need to recalibrate it?
Yeah. Then you need to recalibrate when you change the design curve radius, when you change the train velocity. Okay. But we did this simulation for 3 curve classes for 3 different class velocities, so according to our network characteristics.
Thank you.
Okay. Next question. Next remark, please. So perhaps also another question from me. So which rail grade do you use at RTP?
Which rail?
Which quality of rail? An R220 and R260? What do you use?
It's a 260.
It's a 260
Yeah,
standard grade.
yeah, in every case, in that case. We also have in other different type of steel, but yeah, in this study we only use it 260. Yes.
Okay, thank you. Another question here.
If we have time, you were using the pressures from the SIMPAC, right, to input for your finite element calculations, and that is elastic, right? So your pressures are extremely high, and so then I imagine that your plasticity calculations overestimate the amount of plastic deformation.
Actually, we used the stresses from SIMPAC, and we use fake plasticity models. So we use a contact model which take into account the plasticity, so we limit a little bit the stresses, and the surface contact is a little bit larger for getting the right forces. So
is it somehow empirical, or how do you do it exactly?
This is one of the contact. This is the contact model that we use. This is found in the literature. Basically it's semi-Archian, and so you have your contact patch calculated like semi-Archian, and then you reduce your stresses, and you change a little bit the shape.
Okay, thanks.
Okay, thank you. Any other questions? We still have a lot of time. Here in the back, Carsten.
Yes, my question is to Ali. During your presentation, I think I heard that for the steel to become austenitic, it required a temperature of 400 degrees?
No, for austenitization, the temperature is around 730 degrees.
Okay, I understand that better. So, thank you.
Further questions? So then I also have a question for you. So you said you first tested a long heat pulse and then a short heat pulse. And said the other way around, it would be just one.
It will be all martensite, basically.
So did you test it, or is this?
Yeah. I mean, I reversed the test.
You reversed the test.
But I mean, basically, the tempered martensite again roasteritize and get back to martensite later. So it will be like one cycle with long period.
So would your work also include in the future then testing how these, if you do some repeated loading, how this will behave?
I'm kind of getting close to the end of my project, so maybe not me, but like students in future probably. Yes, this is the plan for future.
A future project at Charmic then. Okay, questions, further questions? Oh, Stuart, sorry. You're sitting too close, I don't see you.
My question's a bit like David's, Gerald here, that you, as I understand it, you've reproduced this cluster A, or you think you've reproduced cluster A from your cluster A and cluster B. Do you understand why you haven't been able to reproduce cluster B in the test rig?
We haven't focused on that cluster B at the moment. One of the problems, or one of the differences between a test rig experiment and the railway operation is that in a test rig, the profile changes during the experiment. So it's pretty hard to maintain high stress contacts over a longer time. Because, that's this change of profile due to plasticity and wear plays a role in the experiment, in the test rig experiment. For the railway operation, MBS simulations, the profiles are not changed. Of course, they do change over time, but those are taken as fixed. And for some of these contacts, they generate quite high contact, at least normal contact stresses at high adhesion values. But of course, there are some parameters on the test rig you can tune. You can play around with initial profiles, for example, to generate or to move the operating point on the test rig to higher stress values.
So the conclusion from that would be that you'll never get B because you can't maintain those high stresses.
Well, we haven't tried yet, but I'm sure that we can shift the operating point towards higher stress values as well.
Further questions? Still have 3.5 minutes. Again, in the back, Carsten.
The question is to Ali again. In one of your pictures, we saw 2 layers of martensite, or one layer was tempered.
Yes.
And that was where the cracks were.
Yeah.
Could you
I mean, as I explained in the presentation, we have the martensite layer. The volume of the martensite layer is larger than the base material, and also the tempered martensite. So the tempered martensite volume is more or less similar to base material. That's the reason that we have compressive residual stresses in the martensite layer, and then right below that, which is the tempered martensite layer, we have the tensile stresses. And that's this stimulates the crack initiation in the...
Okay. Okay, thank you.
Further questions? So then it's also my time to ask a question to Gerald. So Gerald, you said you operated on a test rig. Voestalpine has 2 test rigs. Which one did you use, the old one or the new one? Or let me put it that way. Was this the test rig where they could also apply some slip in the rail wheel contact? And did you test with slip, or was this a slip-free test?
The image you saw on the first slide was a magnetic particle inspection image from a test rig experiment. This experiment was run on the so-called old test rig. For the simulations, it doesn't matter. So, of course, we want to use the capabilities of the newer test rig as well, which allows to apply braking or acceleration moments to the wheel as well.
This wasn't done in this test, so
no,
this was pure rolling.
In this case, it was pure rolling, yeah, with an angle of attack in a simulation.
Okay.
But there are various other parameters you could change.
But you also referred to test rig tests, and also there you had pure rolling and angle of attack, correct?
Yeah.
Okay. Thanks. 1 more minute. 1 more minute. 1 more minute. Any further questions? Any further remarks? Well, if there are no further questions, let's give all 3 presenters a loud applause.